Welcome back to TamTech Academy YouTube e-learning series. In today's video, I'll be walking you through a technical quiz related to refinery operations, which include the refining processes, then distillation, pumps, heat exchangers, and a couple of problem-solving questions. I'll explain not just the answers, but also the logic behind them, and let's get started. So, in the refining operations, the first question is related to mainly the isomerization process. During the questions, I'll also explain some details about the processes as well. For example, the first question is about the main purpose of the isomerization is to increase the octane number, because as we are increasing the octane number of the light naphtha, because the light naphtha is going through the isomerization process, we are making the valuable product from this light naphtha. So that's why we need to increase its octane number. So we increase the octane number of light naphtha with isomerization. For the heavy naphtha, we do it with the reforming processes. We'll go to the second question. Typical feed to light isomerization unit is C4, C6 paraffins. I wouldn't say exactly, because it's mainly the naphtha that we talk, the straight run naphtha right after the distillation column, which is the atmospheric distillation unit. It will first of all see the naphtha stabilization unit, and then we'll send it to the light isomerization unit. It will be wrong, the A. The third question is the isomerization mainly improves ammonia, RON, or cetane. It is the research octane number. Yes, it's the B. That's correct. A common isomerization catalyst is platinum or chlorided on alumina. Yes, that's correct, because we need the acidic site as well. That's why we have the chlorided alumina content. So, by the way, for the most of the refining applications, we have this catalyst. Chloride on the catalyst helps to create, yes, acid sites. That's correct. The sixth question, isomerization reactions are exothermic. Yes, that's correct as well. So we have only one wrong, which is the 5 out of 6. Now coming to the seventh question. The most harmful impurity to the catalyst is water, CO2, or nitrogen. It's free water. Yes, that's correct. But well, if it's like CO or the other content, NOx content, yes, that would be also very harmful for the catalyst as an impurity on the catalyst. Eighth question. Hydrogen is added to the reactor to prevent coke formation, improve selectivity, or reduce corrosion. It's a bit tricky, but the most, I would say, the obvious one from these answers is the prevent coke formation. Actually, we are adding the hydrogen in order to prevent coke formation and also somehow to improve the selectivity in our refinery operations, but the B is correct. Most common reactor type in refinery operations, stirred, moving bed, or fixed, depending on applications again, but I'll also count this as a correct, let's say as well, but this is correct. 10th question. Main objective of the delayed coker is it's to convert residue to the lighter products to get more valuable products. It's correct. Main feed to DCU, delayed coker unit, it's the vacuum residue. That's right. Key products from the fractionator is so the first fractionator. So we have the naphtha, gas oil, gasoline, diesel, or propylene butadiene. It's not definitely it's not correct. Yes, we might have the naphtha, gas oil, or let's say there was other name, the diesel, motor diesel, or home heating oil. That's right. Drum temperature typically is here. It's still, yes, 500 Celsius. That's right. 14th question. Vacuum is a packed column, whereas atmospheric distillation unit has sieve trays. Is it true or false, and explain why? I'll first of all explain if it's true or false. So in general, vacuum columns, they are using the packing to reduce the pressure drop. Because as you know, if we have a sieve trays or trays type of the applications in the columns, they have more pressure drop. Around for each tray, we have, let's say the industrially, we say 10 millibar pressure drop. We actually enter this value around this value, let's say to the simulations when we are designing the columns. But for the packed columns, it's better because they don't have that huge pressure drop and they have less pressure drop. That's why they are using the vacuum columns. But for the atmospheric distillation, we are mainly using the sieve trays. So I would say that atmospheric columns, that they can tolerate more higher, let's say, pressure drops. That's why the trays are used. Now let's see what is written. So it is true, yes. A vacuum distillation column must keep the pressure extremely low. Yes, because even a small pressure drop causes the pressure at the bottom to rise, which increases boiling temperatures. Okay, higher temperatures can damage or crack heavy products. packing is used because it gives good vapor liquid contact with very low pressure drop. It's not always the case. That's why I'll not give the whole point. Like I'll give 1.5 points. As I mentioned, so vacuum columns, they are using the packing because of the pressure drop. And this is actually very critical for vacuum conditions. But for atmospheric ones, we'll say that higher pressure drops are more tolerable. 15th question, how to control pressure at vacuum distillation unit overhead. In general, the pressure is controlled at the vacuum distillation unit with the steam ejectors or vacuum pumps, we can say in the very old applications. And this non-condensable gases, they will be removed via the ejector stage. And overhead condensers, they will help you to maintain the vacuum. So students write that, so manipulate the control valves in the top of the column where the cold water come to the condenser. Okay, valve after reflux. But the thing is that it is for vacuum distillation column, and I expect to have, yes, steam flow ejectors. I'm not sure about this one. That's why it's again the 1.5. 16th question, what are the potential operational challenges in crude distillation unit furnace, and mention at least one and how to troubleshoot it. So it's not only for the crude distillation unit furnace, it is very typical for most of the furnaces in the refinery operations, mainly the coking issue. So the coking is right. In general, to, let's say, to tackle with this problem, on the furnace tubes, and which reduce mainly the heat transfer, let's say, it can be mitigated by controlling the film temperature, or you can increase the flow rate. While it was this way, you will increase also the velocity, or you can do the decoking operations very periodically. So depending on the furnace, depending your operational requirement. And additionally, as I mentioned, so the crude distillation unit, they have the furnace before the atmospheric distillation column because they need to preheat the overall product, and then it will be sent to the distillation unit. If we see coking inside furnace, okay, tubes, heavy hydrocarbons crack at high temperature and form coke deposits on the tube walls. Yes, that's right. This reduces the transfer and increases tube metal temperature. Yes, that's right. TMT will increase tube skin temperature as well. They could be increased. They are the same thing. How to solve it? Lower furnace outlet temperature, perform regular cleaning. That's right. Desalter performance. I'm not sure about this desalter performance because I expect to have some answers related to, let's say, the easy to use or easy to solve with this, let's say, the solutions. It might be correct, like, but I'm not sure. No, the desalter performance, before the desalter performance, mainly we see the furnace outlet temperature, yes, but it's also the rare because we have some spec to achieve, some boiling points to achieve. So that's why I would say performing regular cleaning is more sensible answer to me right now. But also you can change or do the decoking operations frequently. So from this part, I think the refinery is done. Now we'll see how many points. So it will be 2 points as well. So 2, 3 overall 5. 5 from open-ended. And we had only, I think, one mistake. Yes, one mistake. And the 13 questions. So 12 questions is right. 12 multiplied by 2, I think, if I don't mistake. Yes. Multiplied by 2, 24, 29 points. Well done. That's actually a good score. Now we'll come to the distillation operations. In the distillation operations, we'll see actually 2 or 3. Yes, only 2 questions. The first question, how increasing or decreasing reflux to the column affects the column operations? So increasing reflux, in general, it improves the separation and product purity. But always keep in mind that increasing reflux will also increase your energy costs. So the next one, decreasing reflux. It will reduce your energy use, but it will unfortunately worsening your separation efficiency, your separation performance, and it may cause like off-spec products as well. We'll see that so change in pressure in the column distillate can get heavier, residue lighter. Okay, so this is mainly the cut point issue, and fractionation capability issue, which is right. High temperature at the bottom or at top or bottom in the column, increase or decrease separation? Yes, but I would expect to write exactly so what increasing reflux results in the column and decreasing the reflux. In general, yes, I agree that yes, changing the pressure or changing the reflux, it will make your distillate can get heavier or residue lighter and etc. Okay, it will be also half again too. The next question is the weeping, how to prevent this issue. So shortly, weeping occurs when your vapor flow is too low. So to support the liquid on trays, so it means that your mass transfer in each tray will be worsened. So it's prevented by maintaining sufficient vapor velocity and proper tray design. And you need to also control your pressure drop as well in this case. So whipping is when vapor going up inside column is too weak or too slow. Yes, not too weak, too slow. Normally the vapor pushes the liquid up. Keep it sitting nicely on each tray. Okay, this is the equilibrium part, but if the vapor is not strong enough, it cannot hold the liquid. So the liquid starts to fall down through the small holes in the tray, the sieve trays, let's say. If whipping gets really bad, too much liquid falls down at all once. So, okay, just imagine that all your liquid will go down like this from each tray. It means that it is dumping. Yes, I agree. When it happens, pressure drop occurs and separation decrease or stops at all. And how to solve it? Increase vapor amount in the column, decrease Q cold flow rate in condenser, open more reflux valve, yes, close the bit side if you have side steam valve, increase reboiler duty. I agree, definitely. I agree. Very good explanation, by the way. 4 out of 4. And overall, 6 points from this section. Okay, the next section is about the pumps and heat exchangers. So we have 1, 2, 3, 4, 5 questions, I think. Yes, 5 to 6 questions in general. So what are the main stage required data for pump design? Okay, so I didn't ask for, let's say that in general, all the steps, but so what kind of parameters do you need to consider for pump design? First of all, you need to have the specific, let's say the required data, like what are you pumping? What is your fluid? What will be like the fluid properties? Is it really viscous? Is its density like the higher, lower, or something like this? What is the temperature? What is the pressure? You need to know at least this data to start your pump design. So our students wrote no flow, fluid, temperature. Okay, inlet and outlet. Both. Calculate total head needed. Choose pump type. Yes. After having all the required data, you can easily look for the charts to understand that. So what type of the pump you will use? Is it centrifugal? Is it PD type of the pump? But in general, I would say that from the most of the manufacturers, you can easily find on the internet that so for these applications, what type of pump could be used. Check NPSH to avoid cavitation. Actually, this is the heart of the, I would say, the pump design, pump sizing applications, because you need to make sure that your NPSH available will be higher NPSH required. Select right materials, yes, for the pump, but this is not for the process engineers, I would say. No corrosion. Calculate power efficiency peak motor, yes. Flow rate, total head, fluid properties, yes. NPSH available, pump efficiency, power consumption. I agree that these 3 main things that we need to calculate at the end to make sure that our pump design is completed. The next question is the pump curves. So draw pump curves for kinetic and positive displacement. For the centrifugal, the other name is actually kinetic or volumetric was. What type of information we could get from these pump curves? Okay, first of all, I'll see the pump curves. Yes, it's here. So the pump curves, when we say the pump curves, we need the head and the flow rate dependency on the graph. So on the y-axis, as you can see, so we have this kind of the line, which is going like this. For the centrifugal pumps, actually, so the head and the flow rate, they will be dependent in not proportionally. I mean, for example, the head will be like this, 1 over Q flow rate. So as you're increasing your head, overall, this side will be decreasing, okay? It means that at your maximum flow rate, so you don't have any head. At your maximum head, you don't have any flow rate. This is the dependency for centrifugal pumps. But for the positive displacement pumps, yes, I agree that it looks like this. After very, very high, let's say the head, it starts to a bit differentiate, but it is a bit rare case, I would say. But in general, this curve, this graph is correct. And they showed also the efficiency curve, as I see, the rated impeller diameter. Actually, we don't need this rated thing. So yes, the BP is the best efficiency point. We try to operate our pump nearly this area. And efficiency curve, minimum impeller diameter, okay, centrifugal pumps and PD pumps. Yes, that's right. So pump curve show how a pump works at different conditions, agree. From them, we can see how much flow the pump gives at different pressures, how efficient it is, how much power it's using, yes. And by the way, these curves are very important during the design phase, because even after the design, if we have already the pump and we have some change in the operating conditions, like we need to recalculate our NPSH available, let's say, So if it's changed, we still have this MPSHR, which is required, provided by the manufacturer. So we need to make sure that this is greater than required. Because in this case, we'll be making sure that so we don't have any cavitation issue in the pump and it will work properly. That's right. Well done. Overall, this is the 6 points. And from this one, yes, it was also right. 6 points. I write a 12 overall. The next question is the mention most important pump operation challenges, how to troubleshoot. Yes, easily. I was looking for the cavitation. So cavitation, so how we are dealing with the cavitation in general, or I can also give example from the other ones, which are the vibration and also the another one, which is written here, the seal leakage. And solutions surely include that you can increase your MPSS, you can do some change in your operations. If it's possible, you can change some alignments or proper suction conditions and etc. Okay. 4 points, yes, that's right. So I'll not cut any points from the vibration, but it's fine. What do you know about the NPSH and which parameters are used? Yes, what I was looking for is this equation. So for the NPSH available, you need these 4 parameters, which are atmospheric vessel or pressure, head, static suction head, yes, vapor pressure of the liquid, and suction line. Yes, that's right. And this is the open-ended version of the formula, but it's the same. So when you try to make any change, or let's say they move away from the MPSHR, which is the required curve, so you need to do some eliminations or some adjustments on this calculation. It could be either static suction head or suction line frictional losses, I would say, during the operational already conditions after startup. But so if you are not in this phase, like I'm in project execution phase and etc., so you can also do some alignments on the atmospheric vessel pressure, again the suction head, and also the frictional losses. So how you will do it? So you will in general decrease the number of T's, elbows, and etc., or you will not make it them like this pipeline. So you will try to make it straight in order to avoid the mainline frictional losses. Okay. For the next question, the 23rd in my case. Yes, that's right. So which type of heat transfer do you know? We have 3 types, yes, conduction, convection, and radiation. And why do we need the heat exchangers? So because in general, heat exchangers, they are transferring the energy efficiently between fluids and for heating, cooling, energy recovery. So they wrote us the same thing. So what does heat transfer area depend on? Yes, the equation is so simple. Q is equal to UA multiplied by delta T. Delta T is your driving force here. So temperature, inlet or outlet temperature, hot and cold, let's say the differences. U is your heat transfer coefficient. This is the overall one. And A is your surface area. So your surface area, depending on the Q heat duty or heat load, heat transfer coefficient and temperature differences. So in this question, you can also summarize that what U is dependent on, because as you know, for the each conduction, convection, and radiation, we have different laws to follow, and it could be also them written, but anyways, it's also acceptable. It's right. So difference between countercurrent and co-current flow, why it's preferred. So countercurrent flow moves in opposite directions, which is right. It gives better heat or mass transfer efficiency. Co-current flow moves in the same direction and efficiency is lower compared to countercurrent. And what's the driving force? In general, the driving force for heat transfer overall is temperature difference. Yes, delta T that I mentioned before in the previous equation. In countercurrent flow, this difference is larger than in co-current, so it's more efficient. More heat on the same area. So it is right in the case of your Q is the same, Q constant, and your area is the same, by the way. There are some cases, so sometimes even your co-current is better than counter-current, but there are another aspects that we don't want to put the co-current in the heat exchangers, and we prefer the counter-current. But the main principle actually comes from the temperature differences, which is the driving force for the heat transfer. So let's continue. How to increase the furnace efficiency. As you know, furnace is also one type of the heat exchangers, but it's a really big one, furnace or the fired heater, let's say. So it's you can read it about that mainly from API 560 or 660 in a detailed manner, so to see the design and how it's constructed. So the increasing the furnace efficiency, what you need, so in general, you can improve your excess air control. I'll write it here also, air control, excess air control. So enhance your heat recovery, And you can try to maintain your clean heat transfer surfaces, because in the furnaces you don't have only the cooking issue, you have also another problems like sooting. This is another type of the problems you can also see in the furnaces. So for the furnaces, so you need, in order to, let's say, the increasing the lifetime of your furnace, you need to have the clean heat transfer surface area. It's a bit hard to achieve because we are in the hydrocarbons environment and we are discussing very heavy hydrocarbons even sometimes. So that's why it's a bit hard, but we need to follow this. So what is written? Reduce excess air, recover heat with air preheater. Yes. Minimize radiation and convection losses. That's very good point, because in general you need to, if you are able to reduce your losses, so it's a very, very big plus for the for increasing the furnace efficiency. And we have mainly radiation and the convection sections. That's why so they mentioned that minimizing radiation and convection losses. So we don't have conduction as a section, but conduction is possible in the furnace inside. Okay, 3, it's fine. What should be considered in furnace fuel gas composition? Okay, very good question, actually, because we need to be careful here of which parameters are we talking. So first of all, for me, it's the heating value, then your sulfur content, heating value. Then we have some impurities, or let's say the sulfur content mainly. Also, the hydrogen content must be controlled, and you should have some stable chemical composition. Okay. So calorific value, heating value, some impurities, H2S, CO2, H2, okay, especially this one, lead to corrosion, chemical compositions, also flame temperature, some other physical properties. Okay, that's acceptable too. The next one, what are the main parts of the furnace? Burners, furnace tubes, parts. Okay, this is inside, okay, which is okay, acceptable, but I would expect to have mainly a radiant section, and to mention where the tubes are located, then convection section, also stack, draft, burners, air system. Draft system helps move the flue gas through the furnace. Yes, natural or forced. Flue gas outlet, hot gases leave the furnace. Okay, but I'll give only 1 point, because the heart of the furnace is radiant section and also the convection section. They should be definitely mentioned. Only 1 point. So we have only the 2 or 3 questions left, I think. Yeah, 2 questions. So both of them are very simple problem solving, actually, the questions. So we have, imagine a CSTR, which is continuous stirred tank reactor, where your A to B in liquid phase runs isothermally at 350 Kelvin. So isothermal, as you know, means that temperature doesn't change. Temperature is constant. Compute mass or molar balance, both of them are acceptable, and energy duty. So most of the things are given, and this is very simple problem solving, let's say the example, even for the second year or first year students. So if you know about the conversion, you can easily solve this problem. And also the enthalpy, sorry, I forgot to mention. So your feed is given as the pure A, and the molar flow is 3600. Your feed temperature is given. Your reactor temperature is given. It means that, so the change only the 50 Kelvin. There is no need to convert to the Celsius, by the way. You can easily work with the Kelvin. Conversion of A, it's the 60%. So it means that, as it's written from A to B, if your XA is equal to 60%, it means the only 40%, it's not converting. Your reaction stoichiometry is 2:2, or it's just 1:1, as you know, it's just the same, 1:1. Your reaction enthalpy exothermic, HR minus 120 kilojoule per mole A, and negative sign means that heat is released. Yes. Heat capacity, assume for A and B is the same, it's 0.1. It's very simple, as you can actually imagine. We said that you need to perform the mass balance, and then you need to find the energy duty. And we said that there is no heat loss. It means that, so if you have this reactor, I'll use the same reactor picture. So whatever it's coming from here, energy in, it should be equal to energy out. Okay, so now we'll see the mass balance. We said that it is given 3600, and the 60% is converted. So this is right, and it means that the rest, which won't be converted, it will be here. Okay. Next. Now, if we see the general the mass balance for the B, it is written like this. For the energy balance, Q total is equal to Q by reaction and Q change in temperature. So we have FB multiplied by delta H2. FB was 2160, and it was given minus 120, if you remember from this part, the reaction enthalpy. And we need to consider also the additional temperature change. So this is for here. And then Q change is the MCP delta T or NCP delta T, because the CP was given with the mole as well. So 3600, then this one, okay. And there some will give us minus 241.2 something. The thing is that, so I have checked the results. Mine is a bit different from this calculation, but it's so close. That's why I'll give the whole point. It is okay. The last question, it's about the this time furnace tube heat transfer. I would say the a single horizontal process tube outer diameter is this one. Okay, runs through a fired furnace gas temperature 1200, and tube outer temperature is the 600. So furnace gas act like a black or enclosure, so its emissivity is given. It means that you will calculate the radiant heat transfer. Then convective heat transfer is given. It means you will also calculate convection heat transfer. Steady state, no heat generation, Stefan-Boltzmann constant is also given. Yes, it's for the radiation. So the question is, so calculate the tube external surface area per meter length. It is simple. You will do A is equal to pi, the outer diameter. It is for the area per meter. So this is area and per length. Okay. Then the second one, net radiative heat flux, which is so simple. Again, the Q radiation is equal to Stefan-Boltzmann constant. Emissivity, which is given here, 0.8 T. Boltzmann constant is here. T gas minus T surface. You have the gas, you have the surface temperatures as well, and you will multiply by A that you have found before. Then convection. So you have this law, which is the HA multiplied by TG minus TS, the same again. So you have, I think, the H as well, yes, 30. You will put the same and you will calculate the Q. And the total heat transfer, it will be equal to Q total, Q radiation plus Q convection. And in this case also, we don't consider any heat losses. That's why I didn't ask to, let's say, the calculate. Again, the same thing. So A is equal to PD 0L, okay, over L. Net radiative heat transfer. Yes, this is the only, let's say, the harder part. I would say the difficult and the more challenging, time wasting part is to convert your Celsius to Kelvin and find to the fourth degree. That's why it took some time, but it's so easy problem, I would say. Again, we have some differences in the calculations, but I think the methodology, it's very simple. That's why I'll accept it. So this is the last question, I would say. So in general, we had 30 questions, and we discussed some questions from refining operations, especially from isomerization and DCU, delayed cooking unit. And we discussed some distillation problems, especially from the operational challenges. One of them was the weeping, and the second one was the pressure drop in vacuum columns, and also the atmospheric distillation. And for the distillation column operations, we discussed also when you are increasing the reflux or decreasing the reflux, how your separation efficiency will change. For the pumps, we talked about the design procedure in general, what kind of parameters you need to know, and what kind of the pump problems we mainly expect during operational, which was the cavitation. And we said that simply to avoid cavitation, you need to control your NPSH available, net positive suction head. And for the net positive suction head, we discussed the parameters that have been used in the equation, let's say. So the next topic was heat exchangers and furnaces. And for the heat exchangers, we said that there were 3 types of the heat transfer. And then so we discussed the main purpose for the heat exchangers and why countercurrent flow is better than the co-current flow. Then we discussed some furnace efficiency and furnace issues, which was the cooking and sooting problem, but we mainly discussed only the cooking for this type of the lectures. Main parts of the furnace, we mentioned that it should be radiant, convection, stacked draft burners, air register system. And in the last, we had only 2 simple problem-solving examples, which was, let's say, the one of them related to CSTR reactors. We mainly involved the conversion here, and the second one was about the furnace and the convection and the radiation. Very simple, let's say, the problem-solving. And that's for this technical quiz walkthrough. And if you found this video helpful, don't forget to share it with your classmates as well. So if you want more refinery engineering, process design, or interview focused content, you can let us know through the comments and in our 3 different social media challenge that I have added in the description of the video. Thank you very much. Have a nice day to you, and see you in the next videos.